Good morning, Shelby. How you doing? Good. Good morning, Sarah.
Good morning. Section tomorrow, but review Wednesday. Next Wednesday. So, yeah, I'm probably going to start writing this week. I'm so tired. I feel like he's right on this track. The section every 2 weeks, but it always doesn't finish. Okay. Like half ABA, half
well, I did not include the ABA.
Oh.
5 or 6, but ABA is a lot.
Good morning, Hannah.
It'll take us beyond space and time, but
Okay, looks like we've got a full house. we will need to be on a computer that's working with Excel. So if you can log on now and see if you can get to Excel, that would be great. If not, you can move to a different terminal. We'll do a few other things before we get started on that, but we will need Excel working for us today. Okay, and it is 8, so why don't we get started? Good morning, PsycStats. Oh, can we do a little better than that? Good morning, PsycStats.
Good morning.
All right, now we've all showed up. All right, well, hey, happy Thursday, happy 8 in the morning. We love to get together at 8 in the morning for this class. One fun announcement, the nerds will be doing their thing today. I know we have a lot of folks in the room who are interested in neuroscience. They've got a presentation today going on at 4:30 in Burton Morgan, the neighboring building all the way downstairs. They're going to be talking about buzz driving, and they're going to be talking a little bit about alcohol in the brain. I only recently learned that there is a profession that is called a DRE, a drug recognition expert. Who's heard of that before? So there are people who work in the Department of Transportation who will maybe come to the scene of a crime and the scene of an accident and take a look at the drivers and see what kind of shape they're in. And apparently by visual inspection, they can tell a lot about what kind of drug you're on if you're on a drug. And so it's interesting expertise to have. And that person will be joining us today from Licking County's DRE, will be joining us today in the nerd presentation. We also have a couple of students. It will be Allison Murphy and Megan Puritz, who will be making some presentations on alcohol in the brain and buzz driving. So really interesting stuff. Hope you can join us at 4:30 today if your schedules allow. Okay? All right. So we have a lot to do. We thank you all for completing the TED Eds that you've done. We'll be finishing up our conversation on chi-square, which is what we were doing yesterday. And we were doing that to really set the stage for our broader conversation on correlation. Right? So chi-square is a kind of correlation or association. And let's just make sure that we all are on track with the chi-square distribution. Then we'll make our way into the Pearson distribution today. So can we all draw the chi-square distribution in the air? What does the chi-square distribution look like when we draw it in the air? Okay, I see one person drawing it. We had it on the board yesterday. It was the one over there, if that helps. Okay. Oh, can we do, it looks like 3 of us drawing that, and there are 10 in the room. Can we have everybody draw the chi-square distribution in the air? Okay, all right, there we go. All right, and did we say it's positively skewed or negatively skewed? Positively skewed, okay? So I want you to help me draw this thing. I will draw a positively skewed distribution just like the one that you drew in the air. But we're going to try to develop this a little bit more fully. Can you tell me what's on the y-axis? Spell it out if you know it. Yeah, I see the phoneme coming. You were about to make a what letter? Oh, okay, that was just lucky, I guess.
Yeah.
Okay? I saw you go like this. I thought that was going to give me the phoneme I was looking for. Percent. Okay, we'll call it a probability. How about that? Okay, this is high probability, that's low probability. What are some numbers that go on this axis for the chi-square distribution? What's this number? 0. Okay, so and why is 0 and not some negative number? Anybody have an idea about that? Because when we square the values, we wind up with perhaps 0, but something greater than 0, right? Even if we had 2 negative differences, right? If we had an observed minus expected value that just so happened to be negative, when you square that, you get rid of the negative. At least that's true in the real number system, right? Not in the complex number system that has a real and imaginary component, but if we stay in the real number system, we're going to wind up with 0. And how far does it go off in principle? Go ahead, Victoria. Positive infinity, right? So it goes from that range to that range. That's the range that we're working with in chi-square in principle, okay? All right, and how do we label this axis? That's P. What is this? Okay.
X squared.
Okay, or chi-squared. That's my chi. It has a little knob there, okay, that makes it a chi. So this is the chi-square statistic that we would actually compute. It goes from 0, because it can't be negative, to, in principle, up to positive infinity. You never really get there, but that's the way that is extended. And then we sometimes have a line right about here. What does that line tell us? Somebody help us out. What does that line do for us? Okay, it gives us the critical region, right, or the critical value. All right, and there's a critical value that we can obtain. And over here we have, generally speaking, what fraction of the population, or what fraction of the area under the curve? On this side of that line? Yell it out.
5%.
5%, okay? We can say 0.05 or 5%, 5 out of 100. And over here is 0.95, okay? Does anybody remember the Excel command that we would use to get the critical value? Equals? Yell it out. What command might we use to get the chi-square critical value? Yell it out. Yell out the first 3 letters. All right, we got that far. And then it's kind of up for grabs here. It could be, or it could be. Okay, and it actually turns out to be INV, right? Equals chi-in. That gives us the critical value. Okay, let's do that. Critical value. And let's go to Excel. If you'll join me in Excel. And let's see. We'll go to a new Excel. And what we're going to do is generate some different degrees of freedom. You might remember that we have to put in degrees of freedom, and the reason for that might become very obvious, that when we have different degrees of freedom, that's going to generate different kinds of critical values. Okay? All right, so let's do this. Let's just do a little practice inside of Excel. I've got a blank Excel spreadsheet, and why don't we create some random degrees of freedom, which I'm going to put in as DF. And why don't we say here that this is going to be random between, say, 1 and 10. So equals rand between 1, comma 10. Okay? And we can take a few columns here and center them if we think that makes it visually easier for us. And if you hit the F9 key, you're getting different kinds of degrees of freedom. Okay? Okay. And what we might want to do is get the critical value. I'll simply call that crit val. Okay, for a given degrees of freedom. Okay, so right beneath this, we're going to get a critical value, and we'll say this is equal to chi-inv. We'll open a left paren, just like we had done. Is that too small? Maybe I can zoom in. I think people are having trouble seeing that. I go to View, go to Zoom. My system is operating very, very slowly today, so thank you for bearing with me. Okay, it won't let me do that while I'm in the middle of the computation. So our probability is going to be, why don't we say 0.05? And our degrees of freedom is going to be our neighbor upstairs. For me, at the moment, it's 1. It will be a different value for you. Okay? And when that changes to a 5, I get a critical value of 11. Now let me see if I can zoom in. Maybe that's better? Yeah, okay. All right, how many people have that? Okay? And if you hold down your F9 key, we're getting a new critical value. Right? Now, just to give you an idea about what's going on here with the shape of this distribution, it's always positively skewed. It always looks approximately like that. But the extent to which this thing bends, bends in or bends out, is driven by the degrees of freedom. So you're going to get some moving around of this critical value. It's going to be going that way or that way as the degrees of freedom are getting higher or lower. And so we would typically need, if we had 8 degrees of freedom, we would typically need to have something like a critical value of 15.5 in this particular case before we could say that we could reject the null hypothesis. Okay. How many people have that computation going? Okay. And just to make sure that this chi-inv really is the inverse of the chi-dist function, why don't we do this? Why don't we say something like p-value? Okay. And we'll say equals, and we'll say chi, dist, put in a left parenthesis. And now we want to put in the observed value of chi square. Why don't we put in this, right, the value right above it. Put in a comma, and we'll also put in the degrees of freedom, which is right above that. Okay. And hopefully that all makes sense. So if we have 2 degrees of freedom, and we had observed that value, we'd be at the 0.05. That would be at the 0.05 alpha level. We can think of this as the p-value. We can also put it here, parenthetically, the sig value in SPSS. I'll left justify that. Okay, that's the sig value in SPSS. So if we were to obtain a 15.5 critical or observed value for our chi-square and we had 8 degrees of freedom, we would be at the p-value or the sig value of 0.05. And you can hit the F9 key, and that will always stay at 0.05 as the degrees of freedom are changing and the critical value shown here is changing. Okay? Because we had fixed the critical value at 0.05. Who's following that? Is that working? Okay. So, how far you have to go out here is always going to be driven in part by the degrees of freedom, also in part by your alpha level. Okay? And one of the nice things about doing this is we get a feel for this idea that there's a chi-square distribution. Excel has a chi-square dist function, and we can go back and forth on that chi-square function. We can stick in a desired probability and get out a critical value. We can stick in some observed value of chi-square and get the corresponding p-value. We can do that in both directions, the regular distribution function and its inverse function. Okay? Who's all right with all of that? Okay. All right. Any questions on any of that? Okay. All right. So why don't we go and try something a little bit qualitatively different. We had set the stage with chi-square because it was about associations. I'd like to have some conversation now about correlation, and I want to spend a good portion of today's session doing some computation, maybe the last 20 minutes or so. But we did have a lot of TED Ed questions, and I thought the answers that I looked at were really quite good. And some of these are, I think, really interesting questions, and hopefully they force us to go a little bit deeper than we might have gone in Psych 200. Okay, so let's set the stage for that conversation by reminding us of something that we all learned in research methods, was that educators will tell you that we have something like 4 goals for the scientific method, and they are description, prediction, understanding, and creating change. So of those 4, which do we think is most relatable to correlation and why? We have description, prediction, understanding, which is causation, and application. Which is most relatable to correlation and why? Anybody want to help us out with that? It was a TED Ed question. Okay, thanks, Gabby.
I think I said it was mostly related to prediction.
Okay.
Because once you understand it, I guess you can kind of make inferences about relationships if you know the pattern that it's following.
Okay, all right, yeah. So I think that's fair. I would agree that it's certainly most related to prediction. Interestingly, some people would say that prediction typically will precede understanding. So if you can actually create change, you must have some understanding of what's causing what. And in order to understand what's causing what, we have to have some capacity to be able to predict, even if we don't know what's driving the relationship between 2 variables. Right? We don't know exactly what's causing what. We can at least see that there is some kind of correlation. Right? But I agree with that. I think that the best connection there is with prediction. And we're going to spend almost all of next week doing regression, which is really about prediction. And we'll see there's an intimate connection between correlation and prediction, correlation and regression. Okay, here's another ditty from Psych 200. This is one of my favorites when I teach Psych 200. A fundamental concept in psychological science is that correlation does not imply causation. If our students get only one thing out of Psych 100, that would probably be the one thing I'd like them to get. That's not Psych 200, that's Psych 100. Correlation does not imply causation. Can we identify 3 necessary conditions for inferring a causal relationship between variables? Does anybody remember this? Okay, Melanie's got something.
Well, the 2 variables have to be correlated, and then there has to be a time order relationship between the 2.
Okay.
So the one that's the cause has to occur before the effect.
Okay.
And then you have to eliminate all other plausible alternative explanations.
Okay, very nicely laid out. So we do have to have correlation. We'll come back to that. That's one of the 3. We have to have time order relationship. Causes have to precede effects. Okay, that much we know is true. And then also we have an obligation to eliminate all plausible, and I love that Melanie used that phrase, plausible alternative explanations. Not all possible explanations, but plausible ones. We have that explanatory burden. And if you've met those 3 criteria, then you've gone a long way to establishing causation. Who remembers those 3 from research methods? Does that sound familiar to all of you? Okay. All right, so what's interesting was that the very first of those was correlation. Right, so this sometimes confuses students in Psych 200 because we spend a good portion of Psych 100 telling them that correlation does not imply causation. But then we also tell them in Psych 200 that correlation is a necessary condition for causation. right? And sometimes they get stuck on that. Okay? Why might you imagine that they get stuck on that? Well, they think we're contradicting ourselves between Psych 100 and Psych 200. Some idea about why they struggle with that? Okay, let's do this. Just going to jot something down with me. We'll jot down two possibilities. We're going to make something like a Venn diagram. I'll start over on this side. I want you to write the word correlation and put it in a circle or an oval. And over here we'll put the word causation. And we'll put that in its oval. And so we have correlation and we have causation. Okay? Now let's draw a bigger circle around this. Okay? And because we have correlation here, let's put causation. And we'll draw a bigger circle around this one. Okay? And because we have causation here, we'll put correlation. So we spent most of Psych 100 telling them that correlation does not imply causation. Okay? But then we come back and we give them other information in Psych 200 that suggests that there's some contingency between these two. So which of these is actually more accurate? This one or this one? We can say, is correlation a special case of causation? Or do we think that causation is a special case of correlation? What do you think? Yeah.
That one.
Okay. Let's all vote by pointing. How many people are inclined to go with this one? Okay. How many people are inclined to go with that one? And how many people are not sure? Okay. So this is the one that we think that we like. Correlation. If we get this far, things out here are not correlated with each other. Right? Okay. Things inside here are correlated with each other. But something could be here, and we could have a correlation between two variables, but we haven't gone as far as getting all the way to causation. So we have to get at least this far, right? And this comes back to Melanie's first point, that the first thing we have to do is establish some kind of a correlation. Then we'd have to do other things. We'd have to talk about time-order relationship. We'd have to talk about eliminating plausible alternatives. Okay? But this is the kind of conceptualization we want. This is not what we want. It's a little bit unfortunate these two words sound a little bit like each other, just phonetically. I think that creates some of the confusion. But we can still stand by our principle that correlation does not imply causation, and we want to go with this kind of a relationship. Okay? All right. All right, so hopefully that's all a good amount of review for you. Okay, I did want to spend a moment on the notion of parsimony. This is question 3. So a data set can be described by a measure of central tendency. Let's all yell out the 3 measures of central tendency. They are mean, median, and mode. Okay, so we all have that. And then we can also come along and we can describe a data set using a correlation. And to compute something like the regular R statistic, we have to compute 2 means. Right? We need a mean for the x-axis. We need a mean for the y-axis. How does this all relate to the idea of Occam's razor? An interesting philosophical idea, Occam's razor. So on the one hand, when we're doing descriptives, we might just say, here's the mean, median, or mode, one of those 3. Okay? And then we have correlation, which requires us to compute 2 means. It's less parsimonious. Somebody help us out with Occam's razor. Okay, thanks.
It said that you should choose whatever explanation, if there's several that equally explain something, you
okay.
should choose whichever one is most parsimonious or simplest.
Okay, right. Yeah, so it's an interesting idea that all other things equal, and I think the Latin phrase for that is cerebus paribus. Right? So cerebus paribus, all other things equal, the simplest explanation is the best. And that is an important caveat, all other things equal, right? Because you can imagine that there is a more complicated explanation for something, but it actually gives you more explanatory power. Right? So we want to make sure that we are keeping everything else equal, and everything else equal, if we have 2 possible explanations for something, we're going to opt for the simplest. Okay? Now, why do you think, and this is question number 4, why do you think scientists would generally prefer Occam's razor? We wouldn't have to go with that. We could say that we don't really have a preference between more complicated or less complicated explanations. Why do you think scientists might prefer to abide by Occam's razor? Thanks, Gabby.
I think it's because it's like less assumptuous to have like a more direct answer, and that means like less bias.
Okay. It's less assumptuous. I like that. Yeah, so you don't have to make as many assumptions, right? Okay, and as soon as you start making assumptions, maybe you're introducing some possibility for bias. So if we want to rid ourselves of bias, we'd like to make as few assumptions as possible, okay? And so that would be an argument in favor of Occam's razor. Right? All other things equal, the simplest explanation is that. Something else. I think that's great. I think that's really right on track. Are there other ideas? This was question 4 from TED Ed for yesterday. Oh, Karen's got something.
Simpler theories are also easier to test.
Simpler theories are also easier to test, and we like to test theories, right? So part of what makes science is we don't just assert explanations, they have to be testable explanations, okay? And if you have a relatively simpler model, okay, then maybe that's easier to test, okay? I think that's good. Something else? So it might make it easier to test. We might have fewer assumptions. If we had a little more time, I'd like to share with you a video that I put together for Psych 200 that talks about why parsimonious explanations, all other things equal, are probably also more likely to be true. Right? They're more likely to be true. They're more probable. So the word that we're really focusing on is parsimony. What is an economical explanation? But we can also talk about, well, if you have two explanations, one is more complicated, one is less complicated, is one of those more likely to be true, all other things equal? And I think we can demonstrate pretty empirically that other things equal, the more parsimonious one is more likely to be true. Okay, but that actually takes a little bit more time to explain than I'd like to spend this morning, especially since we have really good other answers here, that it's easier to test if we have a more parsimonious explanation, and we're less likely to have bias because we're making fewer assumptions. I think those make a case for Occam's razor just like that. Okay, can somebody share some fun historical fact about Sir Francis Galton? It can be biographical, it can be historical. So he played a critical role in getting the correlational research going for us and correlational analyses. Thanks, Sarah.
I think he was a half cousin of Charles Darwin.
Okay, he was a half cousin of Charles Darwin. That's pretty neat. Something else? Okay, thanks.
He could read by age 2.
Okay, he can read by age 2. That's kind of cool. Something else? I want to take one more fun factoid about this fellow. Lived a long life, and all we know 2 things about him. He could read by age 2. I guess we know 3 things. He played a role in correlation. He could read by age 2, and he was Darwin's half cousin. Do we know anything else about him or a fun historical fact? Maybe about that era? Okay, thanks, Victoria.
I guess I just like how it was phrased. It said Sir Francis Galton researched the power of prayer and concluded it had no effect. So
Okay.
people who were prayed for did not live longer.
Okay, all right. So now you might imagine at the time that he lived, that was more controversial than it might have been today, right? Good for him, a real empiricist. Okay. Let's see. Now we're up to question 6. Unless otherwise stated, a correlation reported in the scientific literature is assumed to be linear, and so that's going to be consistent with the y equals mx plus b equation. Can we generate some novel examples of correlations that we would presume to be linear, and also one that we would presume to be nonlinear? Something that departs from the y equals mx plus b. Somebody help us out with that. Either a linear or a nonlinear correlation. Hopefully these will be novel. Okay, thanks, Hannah.
For the linear correlation, I said, at least in American culture, as temperature outside increases, like the amount of clothing people wear decreases.
Okay. All right, yeah. All right, that's pretty interesting. And you can imagine that you'd hit a floor effect there at some point, right? You just can't go any lower. But generally speaking, that's true, right? And we can count the number of articles of clothing. We can count the weight of the clothing. There will be ways of operationally defining the amount of clothing by weight or by number of articles. Okay, Okay, so that's linear. Can we get either another linear or maybe a nonlinear relationship? Okay, thanks, Victoria.
For a non-linear, I did kind of like how much you eat and your energy. Because if you don't eat enough, you'll kind of be exhausted, but if you eat too much, you'll be like lethargic.
Okay, really good. So you would imagine there might be a curvilinear relationship there. And for those of you who didn't see her, she actually made a bell curve in the air. So started out with, if you're really, really starved, she didn't use that very low energy level, then it's going to pick up, and then at some point you're bloated. Okay, so that works. Okay. Did anybody come up? So that would be a curvilinear relationship. It's probably well described by a quadratic function that goes like this, right? You can imagine some others go like this. Can we come up with another nonlinear case, and we'll see whether it's quadratic or it might have some other kind of form. Not all nonlinear functions are quadratic shape. There are other kinds of shapes too. Okay, thanks.
I don't know what shape it would be, but like the age of an individual and then the amount of sleep they get on average per night.
Okay, the age of an individual and the amount of sleep that they get per night. Did you have an idea about how that?
I thought that like very young people sleep more, and then teens sleep less.
Okay.
And then like middle-aged people sleep kind of maybe like a normal amount, like 8 hours.
Okay.
And then older people, I thought maybe would sleep more, but...
Yeah, I think one of the things we hear about is that older people who are toward the later end of the adult human spectrum, they certainly get less REM. Now maybe they doze off as frequently as everybody else, but they get less REM. And babies get huge amounts of REM. If you look at the fraction of REM of your total sleep duration, how much is occupied by REM, it's huge early on, and it just falls off somewhat linearly. But your larger question was about sleep in general and not REM specifically. And so your idea was it's something like this, here, then down, then up, then maybe down. Yeah, okay, so it bounces a couple of different times, okay? All right, so one other one that's fun to think about. Let me throw this out. Can anybody think of a roughly sinusoidal function? So this is nonlinear, right? I'm drawing a sinusoid in the air. What kinds of things, variables that might be measured by psychologists or by other scientists, they wouldn't have to be psychologists, might be varying sinusoidally? Anybody think of any biological rhythms that might be varying sinusoidally? So you might imagine that menstrual cycles will be varying over periods of maybe a week or month or something of that nature. You might imagine that something like depression is going to be higher in times of the year when there's less sunlight. And if you went over many, many years and you're measuring the amount of depression, as the sunlight comes up, you're going to get probably a dip in depression as sunlight, total number of hours per day goes down. You probably get an increase, and you can follow that across time. So it's interesting to think about. There could be highly patterned phenomena that are of interest to psychologists that are not following linear trends or following nonlinear trends, sometimes trigonometric trends. All right. Let's see. I wonder if some folks can explain the difference between continuous and discrete variables. I wonder if we can put that into words. And then sometimes a picture will say 1,000 words. Continuous versus discrete. Maybe you can give us an example. If we talked about having a continuous variable that ranged between 0 and 10 versus a discrete variable that ranged between 0 and 10. How might those two be different from each other? Okay, thanks, Mom.
A continuous variable would have sort of an infinite or like sort of an uncountable number of values in between.
Okay.
Like 0 and 10, whereas like discrete would be like 1, 2, 3, like
Okay.
maybe the integers.
Maybe the integers could be it, right? It wouldn't have to be integers, but the integers are a very nice example of that. You could step by 0.5, so it's not integers, but still, if you're stepping by 0.5, then you're not going to allow a 0.37, right? You'll have 0, 0.5, 1, 1.5. You won't allow a 0.37. If you had an observation of 0.37, you'd have to classify it down at 0 or up at 0.5, right? So you'd have to discretize that in some way. Okay. All right, let's take a look at just some examples of these. Now people are drawing these. I'm just going to look into Victoria's because she happens to be on the top of this one. And I think we were up to question 8 when we started hitting some draw 2s. Okay, all right, so now we're getting to cumulative versus non-cumulative Gaussians, right? Okay, and what's going to be interesting is as we go through the different Excel functions, sometimes we'll have the opportunity to call for a particular kind of distribution. Maybe it'll be a chi-square distribution, maybe it'll be a Gaussian distribution, and occasionally we'll be prompted by a parameter that says, do you want cumulative or non-cumulative? And you might put in a 0 for non-cumulative, a 1 for cumulative. And this could be true for a Gaussian distribution or other kinds of distributions that we might have. So this is cumulative, non-cumulative. Is that continuous or discrete? Let's all take a look at that. Yell it out. Is she drawn continuous or discrete there? Continuous, right? Okay, those are continuous. And I think if we go back, get rid of that one. I think the next question might be, okay. And here we're going to, let's go to that and take a peek. All right, now we get, and I apologize if that's hard to see, but that is the discrete counterpart, right? So we have discrete distributions and continuous distributions, okay? Okay, then we go to the next one. I think this might also have been a draw 2. So here we're asking for some kind of a negative linear function that's going to be on roughly a continuous scale. So she's put in 60, 70, 80, but the fact that she's drawn a continuous line there suggests that students could have some kind of grade that might be 70.289. I said that's all continuous. Okay. And then what's nice about this is we've asked now for a discrete distribution that's going to be showing a positive trend. And she has that positive trend. And she has discrete categories here, milk, water, and soda. Right? So those are, we might think of those. Clearly they're not continuous. That much is true. That much is true. Did anybody have a different kind of graph? Yeah. Okay, what did you have, Sarah?
I have slightly different. I still have the line, but then for each individual variable, I included there's like a vertical line of 3 different dots.
Okay. So, okay, let me get rid of our bogus correlation causal relationship here, and we'll see if we can get that one going. Well, maybe, how about I just do it this way? Line just drop down, and I'll see what Sarah's got. And that was number 10. Here's 10. And here's draw 2. Okay, all right, so there's a similarity between what Victoria had. The one on the left is really quite similar. There's some similarity to the one on the right also. They both have 3 discrete values. It's not a continuum that we've got there. What's interesting here is that we have only 1, 2, and 3. We don't have any values in between that. And you can infer from this that if you were to have measured 1.5, right, then the level that you would get on the y-axis would be somewhere between what you got for 1 and 2. So here's a mean for 2 on the y-axis. Here's a mean for 1. And 1.5 would be about here. 2.5 would be about here. Right? So what's interesting about this axis is that Sarah has labeled these in a way that one gets the feeling that 1, 2, and 3 are actually on some kind of a continuum. They're discretely sampled on that continuum, right? But they're on a number line. If we do, I don't remember what they were, milk and water, and there was something else. Right? Those are sort of categorical variables, and we wouldn't know necessarily by looking at milk versus water what's halfway between milk and water. I guess you could have a solution that's half milk and half water, but we probably want to have something like this where there's a continuum that we were sampling. And what's really cool about that is you can see that the dots will cluster in such a way that you can't get anything in between 1 and 2 because we're sampling this variable discretely. Who's following that? Is that working for us? Okay. All right. That worked out really well. Okay. So that got us up to number 10. The cross product. The next question was about the cross product. I wonder if somebody can tell us what that is in their own words. We're going to be computing in just a moment the cross product when we compute the correlation coefficient. Somebody help us out with what a cross product is? Okay, thanks, Hannah.
It's multiplying someone's z-score on one variable by their z-score on the other variable.
Okay. Yeah, okay. So all we're going to do is we're going to have, we use the word vector sometimes in statistics. A vector is a list of numbers. So you can think of a list inside of Excel, and then here's another list inside of Excel. And if we take pairs of them, we multiply them by each other, we're taking a cross product. And we're going to do that a lot when we're doing any kind of correlational computation. Okay? All right, we'll take a peek at some other Venn diagrams just to see if we can understand a relationship here on question 12. Okay, and I just happened to be on Sarah from a moment ago, so I'll stay there. So we're going to draw a Venn diagram that at least approximately captures a significant correlation. Okay, and here's a significant correlation, and here's the Venn diagram, and then here's a non-significant correlation, and here's its Venn diagram. Right? So we can think about the extent of overlap. This seems very trivial, and what we might call the bivariate case. Right? We have just two variables, one is x, one is y. That will become extremely helpful, the capacity to write these Venn diagrams, next week when we bump it up a notch, and we're doing not only regression, but multiple regression. And we have one variable that we're trying to predict, that's variable y, and we have a bunch of predictor variables. And we want to see how do they collectively overlap with what we're trying to predict, variable y, but also how do they overlap with each other. Okay, so it's pretty straightforward here in this case. It gets a little bit more complicated when we start adding many predictor variables in multiple regression. By a show of hands, how many people here have done multiple regression before? In this class, you probably didn't do it in Psych 200. Maybe you did it in some other class. Do you remember where you did it? You did multiple regression in cognitive psych. Okay, very good. All right. In the interest of time, why don't we head on over and start a computation. I would like to make sure that we get some practice today computing correlation. So if you'll please join me out on the S drive, we'll go into the resources folder and we'll open up one that says Pearson Practice Set. And I will open it too. And I'll go to View and I'll zoom in. Make it a little bit bigger. Maybe my zoom would be better at 150%. 200 might be too big. And we'll give you a moment for that. And while you're doing that, I'm going to pass out these sheets. If you'll take one and pass it down, this is a Pearson correlation formula. Again, this is a formula that I will not expect you to memorize. As I get into it, it comes back to me, and sometimes I find that I basically, can we pass one forward if you have one? Okay, great. Now, I think everybody's got one. Yeah, you don't have to memorize this. I will hand you this. And tomorrow, because we won't have time today, I'd like to do another variation on this. A couple of ways of computing the correlation coefficient. But we're going to do this manually in Excel. And just to see what the practice problem is all about, we're going to compute the Pearson, that's Carl Pearson product moment correlation coefficient, the R statistic, and we're looking at a relationship between the extent to which our student is worrying versus their concentration difficulty. Is there some relationship between these two that we can find? And there's a very simple Excel command that we can use, and I'll show you that one now before we do the computation. So can we all say equals, and maybe you can tell me, does anybody here know the command in Excel for a correlation? There are actually a few of them that do exactly the same thing as each other. One of them is called correl, equals C-O-R-R-E-L. As in correlation, you go for the first 6 letters of that word. And you stick in array 1, also called vector 1, comma, vector 2. Okay, and we can check that out. We get a correlation here for these two of 0.62. Who's okay with that? Did anybody not get that one? Okay. The other alternative on that, I'll leave that there. I'll go down one. We'll say equals Pearson. That's our old buddy Carl Pearson. And I think we had some fun factoids on him before we got those on Galton. We can put in equals Pearson, and we come up with exactly the same number. So a simple correlation between those two. What I would like to do today is at least begin on the computations that go behind this. Okay? Just like we've done before, how to manually compute a standard deviation. We've done how to manually compute chi-square, a type of association. Now we'll do an association that's going to be based on these two means. Okay? All right, so I'm going to clear out all of that. Okay, and I'm back to looking at the relationship between these two variables. And what I'd like to do is, why don't we create or grab this concentration difficulty? Why don't we move it over a bit so that we can create some manual computations? I'm going to grab concentration difficulty. I'll do a control X so I get a ring around the rosy. And maybe I'll move it over to column H with a control V as in victory. Okay, and over it goes. Okay. So now we can start working on these. So looking at the formula that you have in front of you, you can see that we're going to need to get some SSX's, some SSY's, and so forth. And just to remind you of how we get the sum of squares, there's that simple formula there. So why don't we start to get the deviates for the x variable, which we'll use as worry. We'll see if we can use worry to predict concentration difficulty. Okay? So why don't we go ahead and say that we want some kind of a x mean, and that's going to be equal to average. We'll take an average of those numbers. And I get an average of 5.45. Who can corroborate that number? Okay. So our average score for x is that. And while we're here, why don't we just cheat and we'll do a control C and a control V. We'll paste that spatial relationship into the corresponding cell for our other vector, which is our y vector. This is indexing concentration difficulty, and I get a 5.3. So I've taken the average of those two. Who's got that much? I have two means so far. Okay, real good. Now, why don't we see if we can get some deviates and then also some squared deviates. So this was, as you might remember, a score minus a mean. So we can say something like S minus M. We've done this before. You've even done this on a quiz. So this is equal to my neighbor to the left. Boy, mine is going very, very slowly. My Excel has frozen. Okay. My neighbor to the left minus my x mean. Okay. And we can freeze that and drag it down. I start out with a 1.5 x minus x mean. Okay, I get all of those, and then I can also square those. So these are the deviates, and these are the squared deviates. Okay, so that's simply my neighbor to the left quantity squared. And then I can sum these up, as you might recall. Go back to home. I'll put an auto sum. Sum those up. I might move that down by 1. And I might call this my sums of squares for x. So I'll let you catch up with me. Some of you might be ahead of me. Some of you are faster than I am at doing this. Some of you are still plugging away. But I wind up with a sum of squares for 70.95. How many people got that number? How many people are still plugging on it? It's okay, thank you. We'll take a moment to do that. In fact, if you already have that one, why don't you go ahead and just do the same thing for this variable over here. We're going to do the deviates and the squared deviates for the y variable. Equals this minus its mean. Okay. We'll freeze that into place. Wind up with a minus 3. We'll drag that on down. Okay. We can then say this is equal to our neighbor to the left and squared. And now we have squared deviates. We can sum the squared deviates as always. We get another sums of squares, but this time it's the sums of squares that pertains to the y variable, which we also call the criterion variable in regression. So we have a predictor variable on the x-axis. We have a criterion variable that we're trying to predict, and so we wind up with an SSX and an SSY, and I wound up with 74.2. How many people can corroborate that number? Okay, so many of us are still plugging, so we'll give everybody a moment to catch up on that. If you are caught up, I wonder if you can join me in doing something that isn't very mathematical, but just might help. I always find it's helpful that we will need to focus on these deviates for a moment. So I'm going to highlight the deviates, and I'm going to turn them a different color. It doesn't really matter which one. I'll turn them green. If you prefer red, that's fine. But we want these deviates for x, and we want these deviates for y. We don't want the squared deviates here for the moment. We want just the deviates themselves, not the squared ones. So I'm highlighting the x deviates and the y deviates, not their squared counterparts. Okay, now let's check in and see how we're doing in building some of our critical components, the SSX and SSY of 74.2. How many people have those quantities? Okay. A moment ago, somebody helped us in identifying a cross product, and that was the idea of taking a vector and multiplying it point by point by the other vector. So what we're going to do is take a look at this portion, the center portion of our formula, and we're going to get something called the sums of products. To do that, we first need to get some products. We're going to take an x deviate, that's x minus x bar, that's this green column, and we're going to multiply it by its counterpart over here in y minus y bar, okay? And we'll have a new column that is that product, like that cross product. So we can call this over here product, if you like, or if you prefer, you can call it cross product, because it's going to be a form of vector multiplication. We can call it cross product. And the idea is this will be equal to this green guy over here, 1.55 is what I've got. And we'll multiply that by its corresponding deviate on the y-axis. So for me, that was minus 0.3. It should be that for you also. So that 1.55 minus that 0.3, but we'll put that in as a genotype driven by cell address, not by the actual number, and I wind up with a minus 0.465. Does anybody get that number? So that was green times green, right? That's deviate times deviate. And then once we have that genotype, we can drag it on down. And now we have a whole bunch of products, right? We have one vector times its corresponding components in the other vector. We've done a cross product. And you might remember that when we have negatives, lots of negatives matching negatives, we'll have a negative times a negative that will give us positive. Positive times positive will give us positive. That would generate a positive correlation. According to the formula then, we've done this component. We've gone element by element. We've multiplied the x deviate by its y deviate. And now let's sum all of those up. So we can take a simple sum. Okay? And by the way, I put my cursor right beneath that list, and I clicked on the auto sum. I'll drag it down. And now I basically have the SPXY component. Okay? And I wound up with an SPXY that equaled 45.3. How many people can corroborate that number? Okay? That all worked? It turns out that that is the numerator of our Pearson product moment correlation, or the R value. So I promised on the first day of class that this would always be about ratios, ratios, ratios. If you'll join me down here, I'm in C27. We'll have a numerator, and we'll have a denominator. Okay? And the numerator of our R statistic is very simply this SPXY. So I'll say equals, and I'll click on that. So we're halfway there. We need to figure out the denominator. The denominator is just a little bit complicated. We're going to take the square root of the SSX times SSY. Okay, so we'll do equals SQRT, and we'll open a left paren. That's how we take the square root. Okay, we're going to multiply that. We'll click on that 70.95. That's the SSX. We're going to multiply that by the SSY. We'll close off the right paren. The square root of this guy times that guy. Right? That's what our formula calls for. We hit the enter button. We wind up with 72.55. How many people get that number? Okay. And then our R statistic is simply the ratio, and I promised it would be ratio, numerator divided by denominator, equals this guy divided by that guy, and I wind up with a 0.624. Who gets that number? Okay? And just one more time so we can do our double check. If we do equals Corel, and we went back to the original data, we wanted that vector correlated with, I'll put in my comma, that vector. Okay? And you can see to many, many digits of precision, our manual computations match Excel's computations. So when you put in equals Corel, Excel does all those gyrations just like that. Okay? How many people had manually computed the R's before? Maybe in Psych 200? How many people had not manually computed the R? Okay, so hopefully we learned something new there. Okay, we're out of time. I'd like to start on time and end on time. Thanks for a great session. When we come back tomorrow, we'll do a couple more computations in here. We do have a TED Ed for tomorrow on causal modeling. You are my pilot group on causal modeling. I've not done this one before. There's a nice portion of your chapter 15 that answers most of those questions for you. And most of that stuff is definitional, but I think it will set the stage for upcoming journal clubs, where we'll be talking a little bit about causal modeling in the journal clubs. And I think we've got Gwen on for Monday. Is that right? Okay, thanks. Thanks, everybody, for a great session. Have a great day. I hope you'll join us for the Nerds tonight at 4:30 in Burton Morgan. See you there.